So those who are joining late, we've just recapped yesterday's lecture. So all you need to look at is what is on the right-hand side of the screen. And thank you so much for, I knew there was something I had done wrong. Zoom, record, and share screens is the three things I need to do. Okay, all right, we've managed it for like 15, 16 lectures. Okay, so hopefully this is now recording. Can you see it?
I think so.
I thought you logged in and
Yeah, I can just check.
check now that it's actually working. Good. Okay. So now the partition function, which is formally a functional integral, has now factorized into a product of integrals, because the Hamiltonian factorized and the measure factorized. So this factorized because it's just a sum of terms, this factorized because it's just a product. Then I get now the product on the outside of this single integral here. So there's no sigma of k inside the integral, because e to the minus the sigma is just the product of e to the minus sigma. Okay, so this is just an integral that you learnt on your mother's knee. Okay, so you know how to do that, but there's a complication. Okay, the complication is this. It's not a big complication, but it's something you need to check. So the complication is that we started off with s being a real variable. S is real, but that doesn't mean that sigma is real. So sigma can in general be a complex number. So when we write down d sigma of k, what we actually mean is d derivative of the real part of sigma, okay, times d the imaginary part of sigma L of k. Okay, so think about this, just in case you're puzzled about what I mean. Suppose I had this following integral, d to x. That would be then dx dy, where the vector x is the vector x, y. If I have a complex number, dz, then that is dx dy, where z is x plus I, y. So this integral, they are absolutely ginormous birds. And I hope they're not going to eat us, yes. So the Gaussian integral has real and imaginary parts, and so that means that when we expand sigma of k squared, this actually is the real part of sigma squared plus the imaginary part of sigma squared. Okay, so that we need to take that into account. Okay, so let's now go ahead then and assume that you remember how to do those variables, those integrals. So now we have now for each value of k, there's actually two integrals that have to be done. And in the end, what we are going to end up with is, hopefully I haven't made a mistake of a factor of 2, but it's not impossible that I have. We're going to get 1 over the there is a factor of 2 missing here. I can see that. There's a factor of 2 here. So anyway, when we've done all those integrals, what we're going to get is 1 over the square root of, remember you're doing e to the minus x squared over 2a squared. So that is the square root of pi over a, and so therefore, we can write that 1 over the square root of a is the same thing as e to the half the logarithm of a. So that means that z sigma is then e to the 1/2 the sum over lambda over L is less than k is less than lambda times the logarithm of 2 pi v over r naught plus k squared. So that's what I have in my note. Now, it's not impossible that I've missed a factor of 2 and there's a typo in my book. I've got a vague memory of that. So if that's the case, you need to check that, but it's morally the same as that. Okay, so it's something like that. All right. So now let's do ZS. So ZS, that's the integral over the long wavelength degrees of freedom. So that's e to the minus 1/2 v sum over naught is less than k is less than lambda over L, R naught plus k squared, the absolute value of SL of k squared, like so. And so we can do that integral. Now, let's have a look at this thing over here, because this is where the interesting part comes. So look over here. So you can see that we're summing now in this effective Hamiltonian of over k up to lambda over L. Now, what we're trying to do is we're trying to develop renormalization group recursion relations for, in this case, R naught, in general for U naught as well and for H as well. So we're trying to get a renormalization group recursion relation, and our strategy for doing that is to basically derive the effective Hamiltonian and then read off the corresponding coefficients. So in order to do that, we want to read off what R naught is in the renormalized Hamiltonian. So you might say, well, it's just the coefficient of R naught plus k squared, but it's not. And the reason is this is problem. The problem is that we have a sum from naught is less than k is less than lambda over L, not a sum from naught is less than k is less than lambda. So the original Hamiltonian has naught is less than k is less than lambda. After we've integrated out the high wave number degrees of freedom, our Hamiltonian goes only up to states with k up to lambda over L. So what is our solution? The solution is very simple. It's easy. The solution is just rescale space. Okay, so what do I mean by that? Well, I define a variable k sub L to be L times k. And then if I do that, then in this new variable, then naught goes between, KL goes between naught and then lambda, because the L cancels out. So this is a good thing to do. So if we're going to do that, then we have to ask the question, but SL of K has dimensions as well. Right? It has dimensions in terms of space. It goes as L to the 1 minus d over 2. So it also transforms under this rescaling. So we'd better see how it transforms. So let's go ahead and do that. Has Zoom crashed again?
No, it's not. I was just wondering if you could say something about what lambda is. Like, why does this happen?
Lambda is the coarse graining scale in momentum space. Okay, so I've defined my spin variables. They're coarse grain variables, just like the block spin variables are. So when I write down Landau theory, if you go back to the beginning of the course, when you write down Landau theory, we're not looking at every single spin. We're defining a local coarse grained magnetization. It's coarse grained on a sliding window scale that has some scale, and I'm writing that scale in momentum base. So if you think of the window size as W, then lambda is 2 pi over W. Okay, so did I make it clear? So go back 10 weeks or 8 weeks or something, right? We remember we made a sliding window moving along a spin chain, and we defined a local smoothly varying magnetization. It had a coarse graining scale associated with it, which is how many spins locally I average as I slide this window along the chain. Okay, so every variable here has a scale associated with it, and the spin variable has no Fourier components on a scale smaller than that because you've averaged over them. Okay, so that's what lambda is. So that's how we get our effective, that's how we get Landau theory. Then on top of that, now we're renormalizing Landau theory. So now we're actually taking that description, and now we're integrating out further small wave number modes. Did I answer your question?
Yeah, so I guess the idea is that in this version of renormalization theory, you're rescaling lambda, right?
I'm not rescaling lambda. Okay, let's go back here. Okay, so look at the picture on the bottom of the page. Okay, so there is, so when I write down Landau theory, my coarse grain order parameter is defined with respect to the coarse graining scale, which I've now written it down as lambda, because it's easier to write it in k-space. Okay, so in real space would be 2 pi over lambda. Okay, so that tells me that I originally had a lattice. I had a bunch of spins, and I counted, made some Gaussian window of width lambda, 2 pi over lambda, averaging all over those, sliding that along, creating a smoothly varying function, magnetization as a function of space. So I can do a functional integral because I've got a function. Okay. Then what we did last time, you weren't here, but what we did last time was we said, now we're going to say, now I've got this theory, I want to integrate out the small wavelength degrees of freedom. That means the large K degrees of freedom. So I'm going to define a scale that I'm doing that at, which is little l, which is the analog of the block spin size in the real space RG. And so I'm integrating out this high wave number momentum shell, the one shaded in the picture, and that's what we do.
So like the system is still sort of labeled by lambda, but the rescaling is just removing the.
After I've integrated out the shaded variables, my system now only goes up to lambda over L. I've lost those degrees of freedom. And I can't read off the effective Hamiltonian, the coupling constants, because my new Hamiltonian doesn't look identical to the old one. The old ones summed over modes up to lambda. My new one sums over modes to lambda over L. So in order to make the apples to apples comparison, I actually have to rescale K so that the variable here, look at the left on the right hand side, which I just pointed at, that sum goes from 0 to lambda, not 0 to lambda over L. Okay, did I answer your question? Okay, which part of it didn't I answer?
Now I'm kind of confused because I think K is discrete. So you would still
Well, it is discrete at finite v, but at the end of the day, I'm going to take v goes to infinity. Okay, so that's what the density of states in k-space is. It transfers between discrete sets of states and then groups them together so I can have in a Jacobian, so that I have a smoothly varying k. There's lots and lots of coarse graining going on here in terms of the variables that tell you about the labels of the variables themselves, space, everything. It's a very sophisticated set of limits that we're doing here. Okay? Okay. So, all right. So thanks for the question. And let's go back to where we were. So S has dimensions. So if we do the rescaling to fix the limits of the integral, as it were, the limits of the sum, we also have to transform S itself. So let's see how we do that. Well, we know that S has dimensions of L to the 1 minus D over 2. So we could expect that something like that is going to come in here. Now let's see what actually happens. So what we actually do, this is true, but it's not the full story. Well, it is this is a true statement, but the way we're going to do this is we implement it in the following way. What we're going to say is that when I define a new spin variable, SL, that is a function of the rescaled momentum scale KL, I'm going to say that that is related, of course it's proportional, to my original variable labeled by K, which I called SL prime of K, and there's going to be a factor that comes in there, something that does the rescaling. We're going to work out what it is, and I'm going to call it Z to -1, and I'm going to put it in like this. So this is a factor. These things have to be the same. So this is a factor to be determined. And it has to be determined in such a way. So how do I want to determine it? I want to try to make by making the renormalized effective Hamiltonian look like the original one. Now, the original one had a very special feature. The feature that it had that was special, which I pointed out at the beginning of the class, is over here. So let's put another arrow on this thing here. We chose the coefficient of the grad S squared to be 1, or to be a half. Okay, so every time we do a coarse graining transformation, we have to beat the Hamiltonian that we get down into such a way that the coefficient of that is equal to a half. So we're going to determine this by the criterion that the coefficient of grad S squared is going to be 1/2. That's the condition, the constraint that we're going to use. Okay, and this process has a name in quantum field theory. This is known as a wave function renormalization. Because originally in quantum electrodynamics, that's exactly what this process was. Okay, so Z is called the wave function renormalization. Okay, so now let's go ahead and see what happens to the partition function. So here is the partition function after I've done these transformations. So I'm going to write it down like this. So here's our measure, then e to minus stuff. So I've got 1/2. Then I have my sum over k. I'm now going to write as an integral over k. And now the integral is going to go up to lambda. d kl over 2 pi to the d. Then I have this term over here. Look over here on the left-hand side. I have this thing over here. So I have r has changed into some way that we're going to find out what it is. I'll call it RL. K has changed to be KL squared. So I have that. And then I have SL of KL squared. So that's what's going to happen. Oh, actually, you know what? I've skipped a line. Let me do this. I want to move this down here. I'm going to put this thing down here. Okay, let's fix that up. Let me then right, not skip a step. I skipped a step and it will be confusing. So let me just go back. So I have integral ds, and then e to the minus 1/2, integral from 0 to lambda, dk over 2 pi to the d. Then now I've changed L, K is changed by a factor of L. So I've got a factor of L to the minus D that comes from the measure, from the ddk. Then I have R naught, and then I have K. K squared is then KL squared over L squared, like that. And then I have SL of KL squared, but then I've got this factor of Z over here, and so SL prime is equal to Z times that, so then there's a factor of Z squared that comes in here. So if you look at the coefficient of KL squared, let's have a look at that. So if I look here, I've got minus 1/2, then I have L to the minus D plus 2, like that. That's the two factors of L. Then I have Z squared, and then I have KL squared. So that's the coefficient. So I'm looking just at the KL squared term. Why do I look at the KL squared term? Because once I back Fourier transform into real space, the KL squared term is going to be grad S squared term. So I want the coefficient of this thing to be 1/2. So we want this coefficient. That coefficient has to be 1/2 in order for it to satisfy this constraint over here. And so I can read off from this that that Z, this coefficient Z, has to be L to the power 1 plus D over 2. So when I say 1/2, it's got to be minus 1/2. So that's how I've determined what this renormalization constant is, which is called the wave function renormalization. So this is what Z is. Okay. So now I have the Hamiltonian written down here at the bottom of the page, and this, why did I do all this work? I did all this work because now this is of the same form as the original Hamiltonian. And so I can read off that R sub L, the coefficient here, the T minus TC coefficient, that is equal to L to the minus D times Z squared times the original R naught. And then because of the way that Z squared scales, it has a factor of D in it that cancels out that. And so I simply get L squared times the original R naught. So this is the recursion relation for the coefficient, the coupling constant of the quadratic term. And this makes complete sense because that coefficient, we know, normally goes like T minus TC, which is 1 over the correlation length squared, because the correlation length in mean field theory goes as 1 over the square root of T minus TC. And so we would expect that if it goes like 1 over the correlation length squared, we would expect that as I scale length, it will scale by a factor of L squared. So that's how we read off the renormalization group recursion relations. Now, this is just for the Gaussian theory, okay? And of course, this isn't a really good theory because it doesn't have an ordered state. If I don't have the U naught term, so look over here on the left-hand side, if I don't have the U naught term, then I can't have a theory that has a behavior below TC, because we know that when you go below TC, the value of the order parameter is R naught divided by U naught. And so we need to fix that. So let's go ahead and do that. So this is the general idea. That the Gaussian model is not a physical one, because it has no spontaneous symmetry breaking. So let's just quickly remind ourselves about why I say that. So remember that when we have spontaneous symmetry breaking, what happens is that we start off with our Landau free energy, and now I'm just looking at the spatially uniform case. So we have something like this. That's our Landau theory. And now what happens is when dl by ds is equal to 0, that means that either s is equal to 0 or s squared is equal to minus r naught over u naught. And so this solution, s equals 0, that is true when r naught is positive. In other words, you're above TC. This solution over here can apply when r naught is negative, because I've got minus r naught, so that's a positive number. So s squared is a positive number, and I can take the square root of a positive number. So what that means is that in order for us to have spontaneous symmetry breaking, we need u naught to not be 0. And so if u naught is equal to 0, the only solutions that we can get in the Gaussian model are with s equals 0. In other words, there's no symmetry breaking. So now let's put in the quartic coupling. So this is terrible news, because it means that we absolutely need to consider u naught. So the Gaussian theory doesn't mean anything. And it's terrible news because we know that as we go towards TC, u naught gets arbitrarily large, goes to infinity. And so that means that we can't even do perturbation theory. So the trick is that we're going to do perturbation theory, but we're going to do perturbation theory in 4 minus d dimensions. We're going to do a perturbation theory in dimensions. So we're going to do perturbation theory, and then what we're going to do is we're going to do that perturbation theory in non-integer dimensions. So we absolutely need to consider u naught, but u naught goes to infinity as little t goes to 0. And so the solution, we do perturbation theory in non-integer dimensions. I'm going to show you how we set up perturbation theory, and we're not going to do all of it. We're not going to do the full calculation. You're going to have to look at my book in order to see that. So let's now follow section 12.3.1, perturbation theory for the Landau Hamiltonian, or sometimes known as the Ginsburg-Landau-Wilson Hamiltonian. So we start off with our Hamiltonian, which I'm going to write like this. This is the same Hamiltonian that we had before. we're going to do the same thing that we did before. We're going to start off with k defined between naught and lambda, and S of k has no Fourier components with k greater than lambda. That's the idea of coarse graining. I'm going to use a new notation because the equations I'm going to write down get very lengthy. So I'm going to, when I write down the integral with a lower dimension, with a lower variable k, that means integral from naught to lambda dk 2 pi to the d. That's what it means. And I'm also going to define this to be the integral from naught to lambda d slash k. And when I say d slash k, you know what h bar is. H bar is h over 2 pi. So d slash k is ddk over 2 pi to the d. So the slash means divide by all the appropriate powers of 2 pi. Okay, all right. So now why is this a problem? The technical problem that we have to solve is this. The Gaussian theory was easy. Why? Because we have S of R squared is in our Hamiltonian. We just have quadratic terms. And when I go into momentum space, it stays diagonal in momentum space by Parseval's theorem of Fourier analysis. So this is diagonal. Everything is fine. Everything was separate. That's how we could do the calculation in the Gaussian model. But when we have the quartic coupling term, so that's the Gaussian case. In Landau theory, the full Landau theory, what do we have? Well, we have this term, integral dr S of r to the 4th power. And I'm going to write that in the following way. That is the same thing as integral ddr. And now, if I write down S in terms of its Fourier transform, every single S has got its own Fourier transform variable. So I'm going to get a product of Fourier transforms, and S to the 4th Fourier transforms does not equal S of k to the power 4th, as it did quadratically. So let's see what it is equal to. It looks like this. Integral k1, integral k2, integral k3, integral k4. Then I'm going to have 4 powers of S hat of k, S of k2, S of k3, S of k4. So I have those 4 variables, and then I have them multiplied by all the Fourier variables. So it's e to the I k1 dot r plus k2 dot r plus k3 dot r plus k4 dot r. So all I've done is I've substituted the Fourier transform of S into the expression for the integral dr of S to the 4th. So that's what I have. Okay, now you'll remember that you learned on your mother's knee that the integral dx minus infinity to plus infinity of e to the I kx, that is equal to delta of k times 2 pi. So does that delta look like a delta? No. Okay, so it looks like this. So therefore, let's have a look at then what we get here. So what we end up with then is that this thing is equal now. I can do the integral over r because k is just a label. That just labels the k's. R occurs here, 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 and here. In fact, this thing over here is just k1 plus k2 plus k3 plus k4 dotted with r. So this thing is just the integral dr of e to the I k dot r. That is just a delta function. So I can write this whole thing then now, as the integral over R has gone, I've got the integral over K1, K2, K3, K4. I'm not going to write it all down. Then I've got 2 pi to the d, because I've got d dimensions, ddr. And then I have a delta function, delta K1 plus K2 plus K3 plus K4, like that. And then I have the variables that I'm actually integrating over, which are SK1, SK2, SK3, and SK4, like so. And so that whole thing has just become that. So when I write down what the effective Hamiltonian is now, so then what I have is that minus the effective Hamiltonian in K space is just like this. It's 1/2 the integral over one variable, K, R naught plus K squared times S of K squared. And then 1/4 U naught integral K1 up to K4 S K1 up to K4, and then 2 pi to d times my delta function. And this delta function has a very special significance. We got that delta function because we have a system that is translationally invariant. And because it's translationally invariant, we could do the Fourier transforms of all of these things. And what this says is that if I think of this as being scattering from K modes from one to the other, this thing here says that the momentum is conserved. So I've got these different Fourier components. They're all interacting in a certain way, and the sum of the wave vectors has to equal 0. When the sum of wave vectors has to equal 0, that means that momentum is conserved. And so this is called a momentum conserving delta function. And so you always get this in this sort of field theory. Okay, so now what's the next step? The next step is exactly what we have seen before with the Gaussian model. So what we're going to do is we now decompose our spin degrees of freedom. So our next step is we take the spin variable, and now we're going to write it as SL prime plus sigma of L, where this one is long wavelength. This one is short wavelength. Now, what happens is this gets very complicated. And why does it get complicated? Well, it's complicated for the following reason. In the Gaussian model, the S's and the sigmas did not interact. When I decompose S in this way and multiply it out, there's no cross terms at all. It just splits into a part that depends on the long wavelength plus a part that depends on the short wavelength. But when you do so that's in the Gaussian model where everything is quadratic. So because everything is quadratic, it just sums. But when you have the quartic term, so the quartic term looks like S to the fourth, and I'm writing this S to the fourth as S prime plus sigma prime, and then there's 4 of these things. What we're going to induce are interactions between the S prime variables and the sigma variables. So when we substitute that in, when we expand it out, instead of just saying we can just focus on the short wavelength variables and the long wavelength ones separately, just as a product, now there's going to be terms that couple the two things together. And when we integrate out the short wavelength variables, the sigmas, we're going to get some god-awful mess in terms of the long wavelength variables, because for the short wavelength variables, the long wavelength variables are just some numbers, so you just integrate them out, so you get some god-awful mess, and that's the thing that gives you the complexity of the renormalized Hamiltonian, the effective Hamiltonian in real life. So what's going to happen is that the end result of all of this is going to be that our effective Hamiltonian, or in terms of S, is going to end up looking like this. It's going to end up having a part that just depends on S prime. It's going to have a part that just depends on the short wavelength variables, the sigma. And then there's going to be a part, which I'll call V, which depends on the interactions between the S prime variables and the sigma variables, the long wavelength and the short wavelength parts. And so we can read off what this term is, because when we look at this product over here, we can see that there's going to be terms that couple those things together. Okay. So that's why we end up needing Feynman diagrams, because we actually have to keep track of all of the combinatorics of these interactions between variables with different labels. Okay, so what this actually is, we can read off from here. Okay, but I'm not going to write it down right now. So now what I want to do as a next step is I want to explain the strategy. So what we're going to do is this. We have a partition function. It depends on R0, and now it also depends on U0. So we didn't have that before. This thing is the integral ds, that's a functional integral over the Fourier components of e to the Hamiltonian. Notice that I defined the Hamiltonian over here on the left page. I defined it with a minus sign, because otherwise I know I'm going to miss all the minus signs. So I put it in like that. And then this thing we're going to write as the integral ds of e to the h s prime plus h sigma plus v of sigma of s prime and sigma. So that's what we're going to do. And so when we do that, what are we going to get? We're going to get that the z or R0 mu0 now is equal to the integral. It's going to end up being this, the integral dal s prime, after we've done this integration out. We're going to have e to the h s l prime, so these new variables. Then that is going to be multiplied by a factor of the integral d sigma L of e to the h sigma plus v of s and sigma. So we're decomposing it like this, just as we did before. But the important point is, whereas before this whole thing factorized, now it doesn't factorize. And so this, when we do this integral over here, this integral in green, the answer for this will depend on our variable SL prime. And so because it depends on that, it's going to change. That result is going to add to this Hamiltonian here, just for the purely long wavelength degrees of freedom. So integrating out the short wavelength degrees of freedom will modify the Hamiltonian for the long wavelength degrees of freedom. And it won't just be in terms of a simple rescaling of the space like it was in the Gaussian model, is actually going to be some awful mess. Wait, let me finish my paragraph, please. So, so what we're going to do then, so our strategy is our steps are going to be the following. We're going to do the integral over the sigmas. We're going to do the wave function renormalization. For SL prime, we're going to rescale K, which will give us a rescaling of SL prime. And after we've done that, we will then have a partition function, which I can write as now a functional integral over a new variable L and an effective Hamiltonian at that scale L. And this is the end result. And then from this, we can read off the renormalization group recursion relations. So just like we did before, we defined an average with respect to the small wavelength degrees of freedom. So now we're going to do that here, and then we're going to compute all the terms that we want in a cumulant expansion. Okay, you had a question.
I have a question. So before, when we do the Gaussian cases, the constraint we have is like after we do the renormalization group, we still only have the nearest neighbor interactions like gradient S, right? And then the coefficient there is fixed.
The half, yeah.
The half. So
we're going to do the same thing here.
Same thing here?
Yeah.
That I'm confused. Like there, we don't change. Here, we seem to have like higher order interactions.
We may well get higher order interactions.
But the second order, the nearest neighbor interactions.
Well, we're going to have to wait and see.
I see.
Okay. We have to compute this thing over here at the top of the page in green. This thing.
Yeah.
We have to compute that and see what we get. But at the end of the day, we may get new terms added to the original Hamiltonian, but the way we're going to define our wave function normalization is that whatever is the gradient squared term has a coefficient of a half. Okay, so there's nothing to stop me doing that. Right? Okay, so I will generate new terms. So that's how we're going to do it. So let's now go through. So what we're going to do is we're going to follow the same recipe that we did in real space. So I'm going to define, if I have some variable that depends on a long wavelengths part of the spin variable, I'm going to define the expectation value 0. I'm going to define that to be the integral over the short wavelength degrees of freedom, which are the sigmas. The expectation with respect to the Hamiltonian of the sigmas, then whatever is this function A, now it depends on SL prime and sigma, and then normalized by the integral d sigma of e to the h sigma. So that's just like what we did in real space. And this thing over here, this denominator, this thing is just the partition function of the short wavelength degrees of freedom. So I'll call that Z sigma R naught. That's exactly what we had before. So then if I want to write out what the partition function that I want is, that's going to be Z sigma of R naught times the integral dsL prime of the expectation value, or sorry, e to the SL prime, the Hamiltonian for the original system, and then the expectation value of e to the v taken with respect to the Hamiltonian for the short wavelength degrees of freedom. So that's just exactly like what we did before. And this front term here, this is just a number. This is going to be non-singular. It's non-singular because we averaged only over a block, or we averaged only over a small region of the system, the high wave number degrees of freedom. And so because it's finite sum of terms, it's not singular, so it can't be non-analytic. So that's that term. But it will change the zero of energy. So then, so this z sigma, we already know how to calculate it because we already calculated it. It is the integral d sigma L e to the 1 over v sum over k SL squared R naught plus k squared, like so. And here k, I'm summing over lambda over L is less than k is less than lambda. So that's what that term is. That's what we mean by that normalization factor. When I write down e to the v, I can write this as a cumulative expansion. So this is e to the v naught plus 1/2 expectation of v squared naught minus v naught squared plus terms of order v cubed, just as we had before. And so that means that our partition function is going to be the integral dsl prime e to the whatever is the Hamiltonian for the long wavelength degrees of freedom times e to the v, which is going to equal the integral dsl prime e to the h sl prime e to the expectation of v plus 1/2 v squared minus v squared higher order terms. So that's what my partition function is, and then from this I could then read off what is our effective free energy. So we're going to do this integral. So let's suppose that we've done it. We haven't yet done it, but we will. Once we do that, what is the next step? Then after we've done this, we rescale. So we have, say, Ka goes to L times K, and we're going to do a wave function renormalization on our spin variable. So that's going to be like Z times SL as a function of KL. So these are so on the left-hand side are my original spin variables, the long wavelength components thereof, as a function of K. On the right-hand side are my renormalized long wavelength spin variables as a function of KL, and then there is the renormalization factors little z that we have to put in like that. And then after I've done that, then I can read off the effective Hamiltonian. If I read that off, what I'm going to get is that the effective Hamiltonian at scale L is going to depend on some new spin variables, SL, labeled by KL, all at scale L, and that's going to be the effective Hamiltonian for the long wavelength variables, but now as a function of Z times SL, because originally they were a function of SL prime, now it's going to be a function of Z times S, and then the expectation value of V, whatever that is, plus 1/2 the expectation value of V squared minus V squared, and these are all with respect to the zero, and so that's going to be my variable. Okay, so now we can write this down in original form. So once we've written it like that, we're going to say, well, that thing has to equal 1/2 the integral over k, a function which I'll call u2L, the coefficient of the quadratic term. It's going to depend upon what is the k variable, and then it's going to go as L SL of k squared. Then there's going to be a term which looks like this. It's going to be U4L, the coefficient of the quartic term. Just as you were saying, it may involve factors of k. So I'm writing all of these coefficients with factors of k in them. It's going to, and in fact, what k is it going to depend on? Well, now at quartic order, there's not just one k, there's four k's. So this is going to be k1, k2, k3, k4. It's going to depend on all of these things. And there's going to be in here a factor of 1/4. I'm going to have k1 up to k4. I'm going to have my momentum conserving delta function. Like so. And then lastly, I have my sk1, sk2, sk3, sk4. So what's going to happen is at the end of the day, once I've done this calculation, I'm going to be able to read off that I started off with coefficients R0 and U0, and after I've done all this, I'm going to get a god-awful mess where the coefficients have now gone to wave number dependent coefficients, which I've written like this. And these are the renormalized versions of the coupling constants. So I can now get wave vector dependence in these things in ways that I didn't have in my original theory. Okay, so I'm now going to tell you what the result is when you do these calculations. And then I'm going to tell you roughly how you get that. So once we've done this, what do we do then? So the result of this is once I have this, then that gives me RG recursion relations. And what we're going to find is that my new fixed point for R star is of order epsilon. There is a fixed point for the quartic coupling constant, which is of order epsilon. And if I compute what U2 of k is, that looks like R star plus k squared plus terms of order epsilon squared, and U4 star of k is equal to U star plus terms of order epsilon squared. And then there are terms, there's new terms, U6 star of all the k's. That is order epsilon squared. There's terms U8 star of k, and so on, again, of order epsilon squared. So I generate, just as we did with the real space renormalization group, new terms in k space. The Hamiltonian started off as a quartic field theory, and it's going to end up as a field theory with every term in it generated, with k dependence and everything. It's a terrible, terrible mess. But the good news is that when you're working in powers of 4 minus d, that small parameter epsilon, the leading terms look just like the ones that we already had before. So what we're going to do is we're not going to compute these higher order terms, although that can be done and has been done. We're just going to focus on these terms here. Okay, so now I want to explain how do we compute these cumulative terms? Okay, so let's have a look at the structure. So the structure is going to be this. Remember that this V is defined as 1/4 U0, and then I've got K1 up to K4. Then I have my momentum conserving delta function, like so, and then I have SK1 up to SK4. So that's the thing I've got, and each of these integrals, S of k, is basically the integral from 0 to lambda over L d k SL prime of k plus the integral from lambda over L to lambda d slash dk sigma L of k, like that. So in other words, basically S is symbolically SL prime plus sigma, but this is all under the integration. So then all these factors of four S's, what that goes into is terms like this. There's S prime, S prime, S prime, S prime. That's obvious. Then there's a term for S prime, sigma, S prime, S prime. There's a term 6, S prime, sigma, sigma, and so on and so forth, just doing the binomial expansion. And the thing is, remember the sigmas and the S's have different regions of integration. One is from naught to lambda, naught is less than k is less than lambda over L. One goes from lambda over L is less than k is less than lambda. So we have to keep track of the k arguments of these integrals. So you can see that you get combinatoric terms from this expansion, and then you also have to do integrals. So let's have a look at what those integrals look like. So when we have to do calculations, let's have a look at expectation of v, for example. Let's just have a look at this simple one. Okay. So this, what we're going to do is we're going to get a bunch of terms. So the expectation value only integrates over the sigmas. So what we're going to get are terms like this. So I'm going to get u naught over 4, the integral from naught to lambda over L, d slash k1, integral from naught to lambda over L, d slash k2, integral from lambda over L, d slash k3 up to lambda, integral lambda over L, d slash k4 lambda, 2 pi to the d, delta k1 up to k4, and then that's going to be multiplied by what? Well, the first ones are two factors of SL prime of k1, SL prime of k2, and then sigma L of k3, sigma L of k4, and we're doing the expectation value of this with respect to the 0th order Hamiltonian, so we have to put an angle bracket around those terms over here. So we have to do that integral. S prime is just numbers as far as the integral over sigma is concerned. Remember that this thing is only integrals over sigma. So when we do this integral, what we're going to get is something that's going to depend on what? Well, it can't depend on sigma because that's the variable of integration. It can only depend on k3 and k4. So when we do this integral here, this is some big mess that depends on k3 and k4. So then what we have is u naught over 4, integral from naught to lambda over L, d slash k1, d slash k2, SL k1, SL prime of k2, the long wavelength degrees of freedom, and then times some big mess of k3 and k4 times the delta function, the 2 pi to the d delta function. And so this thing then is going to be once I've done that integration, this thing here is just going to end up being some big mess of k1, and K2. And so that is then going to give me the contribution to U2L of K. That's how I'm going to get it. And then this thing over here, after I've done the rescaling, is going to end up being SL of K squared after I've done the rescaling. Okay, so what does it look like? So you have to do this, and it's you know, it requires a calculation, and it's in my book. Okay, so let me tell you what the result is. To order V, here is the result. We have U2L. I'm putting a 1 here because this is the first order calculation. It looks like this: R0 L squared plus KL squared plus 3U0 L squared, the integral from lambda over L to lambda d slash K over R0 plus K squared. And U4 of L to this order is just U0 L to the power 4 minus D, which is U0 times L to the power epsilon. That's what you get. And this is what we saw when we last time when we had our intuition about what is happening in the epsilon expansion. We saw that we guessed this term here, we guessed. And the significance of this is that when you look at the renormalization group flow equation for this quartic coupling, it doesn't have a fixed point. So it's useless. There's no fixed point at order epsilon. So we have a big problem, is that as we guessed, from dimensional analysis, this is useless because there is no fixed point at order epsilon. And so that means, okay, now you have to go and do the calculation to order V squared. Okay, all right. So I'm now going to write down for you what happens when you do this. Okay? So what I'm skipping over is the process of how we do all these integrals. The way the dimension comes in is all these integrals are integrals ddk. Integral ddk is k to the d minus 1 dk in polar coordinates. The integrands are all rotationally symmetric. And so what we do is now we then treat d as a continuous variable and do the integral as if d was a continuous variable rather than being an integer. And then we analytically continue to epsilon equals 1. Okay. So the strategy, integral d dk goes to integral k to the d minus 1 dk, treat d as a real variable, and then in the end, set epsilon equals 1 or not. So let me give you the renormalization group recursion relations, and then we will quit for today. Okay, and they're pretty awful. So R prime looks like this: L squared times R naught plus 3 over 4 pi squared U naught over 4 lambda squared 1 minus 1 over L squared minus 3 over 2 pi squared U naught over 4 R naught log L, that's natural log. And then there's higher order terms, order epsilon U naught, R naught squared, U naught, and so on. And then U prime over 4 is equal to L to the epsilon times u naught over 4 minus 9 over 2 pi squared u naught over 4 squared logarithm of L plus order epsilon cubed, stuff like that. Okay, so those are the renormalization group recursion relations. Okay, and what we have to do, so all I did was do the integrals, okay? And it's like 20 pages of algebra, you just have to do them. But once you've got that, all we have to do is exactly what we've done before, find the fixed point, find a linearized RG, read off the critical experiments. And that's what we're going to do next week in week 10. Okay, so week 10, first lecture is going to be, we're going to finish this. And then the second lecture in week 10, I'm going to then show you how you can use the normalization group to do something completely different, solve differential equations. Okay, you don't have to do it just for stat mech, you can do it for other things too. And that's what we'll do the last lecture. And then the week after that is when you guys are going to have the final exam and you're going to present your term papers and give your little, we'll have a little mini symposium. Okay, so that's it for today. Let's turn off the recording.